Okay, welcome to the temperature notes review. If you remember from the heat notes, we did mention temperature again earlier, so I call this kind of the temperature revisited notes because we've definitely spoke about it briefly before. If you recall, the definition of temperature is the average amount of kinetic energy in the particles of a substance, not the total, and that's a big difference in what that really means. If you remember back to what I was saying in the heat video about the Bill Nye video, and he has the ice sculpture, and he's trying to melt it with a match. And the match has a much higher temperature because the kinetic energy of the particles in the match are much, much higher. So they're definitely moving faster. That is definitely 100% true. So therefore, the match has a higher temperature. But because the ice sculpture has so many more molecules in it, it has more thermal energy total. And that's really the way you have to think about temperature and thermal energy. Temperature is the average amount of kinetic energy in that substance. But thermal energy is the total amount. Iceberg or the ice sculpture has billions and billions of more molecules. So even though they're not moving near as fast in kinetic sense, they are still so many more of them that if you add it all up, it has more thermal energy. So remember, kind of more of like the total versus the average. So you're all very familiar with temperature and the everyday life, like a cooking thermometer, right? It measures the average kinetic of a chicken or something like that. This is a thermometer used in science labs oftentimes. This is one of probably more familiar with at your house. This is your standard digital thermometer. Gives a very accurate reading for a human. And of course, this is just like your classic thermometer over here. There are three temperature scales used in the world. Three main ones, I have to say. There are other temperature scales used, but not widespread. The three temperature scales are Fahrenheit, Celsius, and Kelvin. Notice how they're expressed. Fahrenheit is always degrees Fahrenheit, Celsius is degrees Celsius, and Kelvin is just K. There is no degree on Kelvin, so you wouldn't say 43 degrees Kelvin, which is kind of hard to get out of the habit of doing because when you say temperature, everybody wants to say degrees, and even I do that too, so it's not wrong to say it, but that's not technically how it's broken into different units. Here you can see some good comparisons. You can also see some good comparisons of the three different temperatures in section 10.1 in your textbook. They have a really good little breakdown. Let's move on to just Fahrenheit. There's not a tremendous amount to say about it. It was created by a guy in Britain. I forget his first name, but we use it in America, and we've used it in America since the colonial days, because Great Britain, who obviously was the main contributor to the U.S. colonies, I hate to say exclusive, but main contributor to the U.S. colonies, used Fahrenheit system at that point. The motherland of Great Britain has since changed to Celsius and does not use Fahrenheit system anymore. Used very rarely outside the United States. The only place it's really used outside the United States are United States territories like Puerto Rico or Guam or something like that. I'm sure that the people in Canada are familiar with it simply because they're on the border of America, but I would argue they don't really use it as much as we do. It's not a bad system. It's just the system you're used to. It's not a very good system as far as understanding things in relation to water, for instance. Celsius is based off of water, which is, in my opinion, works out genius because this is what we really use it for, or what we really use temperature for, and it has everything to do with water. 0 degrees. Ice melts. Well, in Fahrenheit, 32 degrees, ice melts and water freezes. So it's kind of one of those things where 32 is not really a round number. 0 is nice and round, and I don't mean just the shape of it, but it's not a, weird number like 32. And then you have 100 is where it boils. It just makes it very nice. And the guy who invented Celsius, I think his name is Andreas Celsius, and based it off of water. Water boils at 100, freezes at 0. Simple enough. And we use it in science. In the U.S., we use it a lot. We use it especially in classrooms. And it's used mostly by the public in all of the countries except for America. That it's not to mean that America's wrong and they're right. It just, it's just the differences in histories as far as why we use it and so forth. But it is an easier system to really understand if you really want to be honest. But, I'm not going to dog the Fahrenheit American system because, to be honest, it's the system that I know. Because, obviously, I grew up in America and it's the only thing I've ever really used. The only time I ever really use Celsius in a regular day-to-day life is in the science setting. And the last temperature scale is more recent. It's called the Kelvin scale, and it's the official temperature of the International System of Units, which is what everybody in the world tries to use. But we don't really use the Kelvin, and it's not a practical unit for your everyday temperatures. Because if you'll look over here, water freezes at 273 K and water boils at 373 K. It doesn't really make a lot of sense as far as using it based on water, which is more familiar to your average person. But what K is really helpful for is this idea of absolute zero. And absolute zero is what the Kelvin scale is based off of. 0 Kelvin is absolute zero. Which is the point where atomic movement or kinetic movement of an atom or a molecule stops. Now, if you'll remember, I've said even cold things like ice have molecular movement where the molecules are moving a little bit. Well, theoretically, there's a point where it will be so cold that atoms will not even be able to move. If they do not move, then they will not have any temperature. Why? Because that's what causes temperature, is the kinetic movement of things. So the faster a particle moves, the hotter it is, right? The slower it moves, the less hot it is, right? So if you stop it, it has no heat. It is 0. So theoretical at this point, not quite possible. We like to talk about it because the entire Kelvin scale is based off of this theoretical point. So, and it's really used mainly in the science industry, and more specifically in astronomy, if you really want to know, because we like to use it to identify how cold planets are and so forth. And it goes way high too, obviously, and it's a lot easier to use one scale for astronomy like that, talking about a cold planet or a super hot star on the other end of the Kelvin scale. So, alright, well, we'll stop it there. Please make sure you watch the heat notes video as well. They both need to be watched in order to prepare you for any kind of heat assessment. So, alright, I hope you enjoyed the video, and I will catch you in class.